So, welcome to London Learning Lean. It's lovely to be back in London, learning some Lean. Next week, we've got Joy Hu and Runchang Li, who are going to just tell us about their work formalizing the Gaussian measure in Lean. But this week, we're very pleased to have Jujian Zhang, who will tell us about his fabulous recent work on flat modules. There you go.
Thank you for the introduction. So the title of this talk is flat modules, but I will only cover like 8 equivalent definitions of flat modules. So how do I get to the next page? Okay, I just left click. So if we fix an arbitrary commutative ring with unit and we call it R, and if M is an arbitrary module, we know that tensoring with M is always right exact. That means if we have an exact short exact sequence, 0 to A to B to C to 0, then we tensor this short exact sequence, we get another sequence, which is 0 to A tensoring M to B tensoring M to C tensoring M to 0. We can still know that the kernel of F tensoring with 1 is the same. Sorry, the image of F tensoring with 1 is the same as kernel of G tensoring with 1. And if G is surjective, then G tensoring 1 is still surjective. But it is not necessarily true that the exactness is preserved on the left-hand side. This is what we call tensoring with M is always an right exact functor. But here is an example of a Z module that fails to be right exact. For example, we consider Z mod 2, then 0 to Z to Z to Z mod 2, where the first map is defined by M sending to 2 times M is exact. However, if we're tensoring this short exact sequence with Z mod 2 again, the resulting sequence will be something like Z mod 2 sent to Z mod 2 sent to Z mod 2, where the first map is actually 0 because, well, in Z mod 2, if you times 2 by something, it is actually the 0 map. So it is definitely not injective. This is an example why it is not left exact. So what kind of criteria should M satisfy so that tensoring with M is exact? We call such modules an exact module. So sorry, we call such modules a flat module. So, well, if tensoring with M is exact, then certainly it is exact. So in Lin, we say it as tensoring right with the R module M is an exact functor. Well, since tensoring with M is always right exact, so it is actually suffice to check that the first map is injective. If the first map is injective, then tensoring with the identity is still injective. So this is something we call tensoring with M preserves monomorphism. So in Lin, we just say that if N and N prime are 2 R modules and L is an injective linear map, then L tensoring with the identity function, identity linear map is still injective. And we can reduce this condition even further. Instead of checking for every N and N prime, we can just check that the ideals of R are I, and we can check if I tensoring M embedding to M tensoring M is an injective function. It is in fact that will in fact be sufficient to say that tensoring with M is an exact functor. And we can do even better than that. We can check instead of for every ideal, we can just check for every finitely generated ideal. If I tensoring M if I tensoring M embedding to M tensoring M is injective, then it is sufficient. So just by pure logic, we can see that 1 if and only if 2. That's because tensoring with M is always right exact. We can see that 2 implies 3 and 3 implies 4 because, well, 3 is just a special case of 2 and 4 is just a special case of 3. So we will now first see how the fourth condition actually implies the third condition. So if we have an arbitrary ideal I, then the set of all finitely generated subideals of I, that means for every finitely generated ideals J, that is literally a subset of I, we can order this set with respect to inclusion. And this ordering is actually directed, meaning if we have two J and J prime that is finally generated and is a sub-ideal of I, then J supremum of J prime is another finally generated sub-ideal of I. And we can, in Lin, we just create a new structure called finally generated sub-ideal. And this two ideal just means, well, two ideal just means what it is as an ideal of R, and we require it to be finally generated, and we require it to be smaller than I. And we can prove that it is a directed system. And so the first thing we can see is that why do we want direct system? Is because an arbitrary colimit sometimes can be very hard to understand. But if we're just thinking about colimits over a direct system, then the concrete representation of this colimit is actually just a direct sum quotient by some equivalence relations. And when we consider this arbitrary ideal I as a submodule of as an R submodule, then I is actually isomorphic to the colimit of all the finitely generated sub-ideals. And to prove this, we can use the universal property of colimits. So from right hand side to left hand side, because there is always an obvious map from J to I, because J is smaller than I. We can just use this collection of map and let this map descend to I. And from left hand side to right hand side, if we have an arbitrary element small I in the capital I, then the principal ideal generated by this small I is for sure smaller than I, and it is finally generated. So there is a map from this principal ideal to the collections, to the colimits over all the collections of sub-ideals.
You have to prove it's R linear.
Yeah, you have to prove that it is R linear. The proof is doable. It's not too bad. So the corollary here is that I tensoring with M is actually can be realized as a colimit tensoring M. It's not really a corollary because it's actually a definition, but and yeah, and this is the implementation. So the direct limit is just for all the finally generated sub-ideals of I, if you just take I as an ideal, and this lambda ijhij is just to prove that this respects the ordering. So this from as direct limit is the map from right hand side to left hand side. So you just use the universal property to lift a bunch of obvious embeddings, and the other direction is much harder because you need to construct this principal FG sub-ideal is just literally the principal ideal generated by R. As Kevin said, you need to prove that this is R linear. So it's slightly harder. But the underlying function is just sending each R to the principal ideal R. And another ingredient we are going to be using is that colimits over direct systems commute with tensor. Well, there are actually better ways to prove this than the proof I present here, because tensor is always right exact, so it actually preserves all finite colimits. So yeah, but this proof here is using just using universal properties of all kinds of things. So so consider if we have an indexing set called I, and we are considering the colimit over I tensoring with M, and the colimit of I tensoring with M. The forward direction, we first need to use universal property of tensor products. So we actually need to construct a bilinear map from the colimit over I to M to the collinear to the colimit of I tensoring with M. So for this, suppose we have a small I in this indexing set, and an element of this small I, and we call that element X. Then tensoring with X is a linear map from M to M tensoring with small I, and M tensor with small I is just a component of this colimit. So there is an obvious map there. And the other direction, we just use the universal property of colimits. This is because, well, I tensoring with M, small I tensoring with M for each I, there is a obvious map sending, well, just by tensoring with the obvious map from small I to the colimit with the identity map from M to M, and this is a family of map, then we can just use the universal property of colimit again. So the corollary is, well, we know that I tensoring with M is colimit of all J tensoring with M. So now we can move the brackets around to form that, well, I tensoring with M is actually isomorphic to the colimit of J tensoring with M, where J is all the finally generated subideals of I. And yeah, forgive me for this terrible name because I couldn't figure out any better name. So this is just the is it forward or the backward direction? Let's see. It is the forward direction. It is the backward direction from the colimit of I tensor M, from the colimit of brackets I tensor M to the brackets colimit of M tensor with M. So yeah, it's you need to first use the you need to use both the. Oh no, yeah, this is the backward direction. You just need to use one universal property, just the universal property of colimits. But for the other thing, you first need to use the universal property of tensor product. Then you need to use the universal property of a colimit. And well, it's you can calculate that the embedding I tensoring with M to R tensoring with M factors through the isomorphisms from I tensoring with M to the colimit of J tensoring with M. So now if you want to prove that this is an injection, so if I tensoring with M to R tensoring with M is an injection, we just need to prove that this iota bar is an injection. But to prove that iota bar is an injection is easy because each component map J tensoring with M to R tensoring with M is injective by the assumption of force condition. Yeah. So this is how you show that the force condition is and the third conditions are actually equivalent. And now we need to show that the third condition and implies the second condition. Well, maybe I should remind what the third condition is. Third condition just says the map from I tensoring with M to R tensoring with M is injective for every ideals, and the second condition is no. No, sorry. Oh yeah. The third condition is I tensoring with M to R tensoring with M is injective for every ideal I, and the second condition is for every two R modules N and N prime. If L is a injective linear map from N to N prime, then L tensoring with 1 is an injective map from N tensoring with M to M tensoring with to N prime tensoring with M. So we first define what a character module is. For an arbitrary R module M, the character module M star is just all the group homomorphism from M to Q quotient by Z. And this M star has an R module structure by defining the R times F is the function that's sending M to F of R times M. And in fact, this character module thing is actually functorial, because if L is a linear map from N to N prime, then there is a obvious map from N prime star to N star by defined as composing with L. So this is so taking character module is actually a contravariant functor. And the nice thing about this functor is that it actually sends monomorphisms to epimorphisms, or in another word, it sends injections to surjections. The proof is that the key part of the proof is to realize that Q quotient by Z is actually an injective group. So if G is a group homomorphism from N to Q quotient by Z, then G factors as N to N prime, then to G bar. and we can show that LG bar is G. So Q quotient by Z is just a red circle. No, we have this in MathLib, but because we are working in higher universe, so we need to lift it. and the character module is just M to the rational circle, and it has a R module structure. So the nice thing about character module is that if M is a non-zero element, then there exists some character such that H applied to M is not zero again. So here we use again that Q quotient by Z is an injective group. So to construct such an to construct such an H, it is sufficient to construct a map from just the submodule generated by M to Q quotient by Z, with the property that H prime applied to M is not zero. So the construction of H prime depends on either M is the additive order of M is finite or infinite. In other words, it depends on whether there exists some case such that K times M is actually zero. So if M has finite order n, then H prime can be defined as K times M sends to K divided by n mod 1. And this is well defined because if K times M and K prime times M are the same elements in the principal module generated by M, then actually K minus K prime will divide them because n is the order. So we will know that K divides n and K prime divides n are the same thing when you take modulo 1. And if M has infinite order, then essentially such K is unique. So you can just K divided by any prime number. And yeah, this is the proof. So the takeaway here is that add order of will give you 0 if M has infinite order. So you can just do it by cases. Another ingredient we will be using is that the tensor functor and the home functor forms an adjunction. So if R and S are two commutative rings with units, and X is an RS bimodule. So because we're only, well, I am only considering commutative case, so it doesn't really matter if X is left module or right module. So if X is an RS bimodule, then right tensoring with X is a left adjoint to the home functor. Note that the tensoring happens in the R modules, and the whole home functor happens in the S modules. And so
Where to where?
Oh, I'm explaining below. So if Y is another R module, then Y R tensor with X is actually an S module, and the S module structure is given by S times Y tensoring with X. It's just Y tensoring with S times X, and all the S linear map from X to Z actually forms an R module. The R module structure is given by R times L defines a linear map sending X to L applied to R times X. So we just need to prove that if Y is an R module and Z is an S module, then if L is a linear map from Y tensoring with X to Z, then there is a map from Y to the home of X to Z, and this map is given by, for any small y in Y, you can define an S linear map from X to Z, just given by sending X to L applied to the pure tensor Y times X, Y tensoring with X. And conversely, if we have any R linear map from Y to the home XZ, then we have a linear map from Y tensoring with X to Z, given by if we have a pure tensor Y tensoring with X, then L applied to Y applied to X is a member of that. So just by plugging in R to be R and S to be the integers, we can see that all the R linear maps from N to the character module of M actually comes from the character module of N tensoring with M.
You get there isomorphic.
Well,
oh, it's
exactly this is just
the adjunction.
This is just home that MQ tensoring by Z. Yeah. And well, this is just showing why this adjunction is not trivial, because the tensor product dot lift is taken from MATLAB. You will see that F is required to be R linear and R linear, but we actually want an R linear and an S linear map. So when you define this map, you actually need to go inside to see how the tensor product is actually implemented. So it's implemented as a list quotient by something I don't actually understand, but I just copy and paste from MATLAB. Yeah, and feel all the stories. Yeah, and this is a theorem due to Lambach. And Lambach said that if the character module of M is an injective module, then M is flat. In fact, this works also in the other direction. So M is flat if and only if its character module is injective, but we only need one direction, so I only prove one direction. The other direction, I think, perhaps is even easier.
And flat here means injective.
Flat means flat here means 3.
Oh, flat means 3.
Yeah.
Oh, okay.
No, sorry, flat means 2.
Right.
Yeah, flat means 2. Yeah, yeah, flat means 2. So if L is a injective map, then L tensoring with 1 is the injective map. So now we consider if A and B are 2 R modules and L is an injective R linear map, then let's just suppose the kernel of L tensoring with 1 is non-trivial. So Z is some non-zero element that get vanished. Then by the previous one of the previous theorems or lemmas, there will be some character of A tensoring with M such that G applied to Z is non-zero, because we assume that Z is non-zero. Then we can define a linear map F from A to the character module of M, defined by given any small n and any M in M, we can just we can just evaluate G with A tensoring with M. And since we assume that M star is injective and L is injective, or L is a monomorphism, this F will factorize through some F prime that is from B to M star. So let G prime be the corresponding map of F prime under the previous isomorphism, or under the previous bijection. And then by writing Z as a bunch of as a sum of pure tensors, then because Z is in the kernel, we know that L tensoring with 1 applied to Z is 0. So we can actually see that G prime evaluated as at the sum of LAI tensoring with MI is G prime of 0, which is 0. And next page. But on the other hand, G prime of or G prime applied to this sum, because G prime is preserves addition, we can just put the G primes inside and use the adjunction. We see that the sum of G prime evaluated as LAI tensoring with MI is just the sum of F prime of LAI applied at MI. Then by definition of F prime, this is literally just F applied to AI applied to MI and then add them together. Then by definition of F, this is just the sum of G evaluated as AI tensoring with MI. Then we can put the G back up front, and this is just G that. But by the choice of G that shouldn't be 0, so we get a contradiction. So we know that the kernel is actually trivial.
Do you think you really use the law of the excluded mode? Do you think really you just prove that for all G of Z is 0?
Maybe. Yeah, but it essentially doesn't matter, because I'm going to use the bias criterion in this slide, and bias criterion use Zorn's lemma extensively. So it doesn't really matter what the previous proof was, how the previous works. So the corollary is that if I tensoring with M to R tensoring with M is injective for all ideals, then M is flat. This is because by bias criterion, if we want to show M star is injective, we just need to show we just need to show this R to M star restricted to I to M star is surjective for all ideals I. This is what bias criterion is saying. And so now we just fix an ideal I and let F be the let F be. So we fix an ideal I and we pick an arbitrary F prime from I to M star. We want to find an R to M star which restricts to the F prime. So given an F prime, we can find a corresponding map from I to M star by adjunction. But since iota, iota is injective, then we said that taking character module is a contravariant function which sends monomorphisms to epimorphisms. We know that iota bar is surjective, so there will be some character of R tensing with M such that iota bar of capital F is F prime. Then we use adjunction again to find the map from R to M star, and that map will work. So now we have finished to show that 1, 2, 3, 4 are all equivalent. Then we were going to see how we can use the calculation of Tor function to prove flatness. It should intuitively make sense because Tor is defined as the left-derived function of tensing with M. So if tensing with M is an exact function, we can see that the higher Tor will all vanishes. So this is equivalent definition 5. So from all higher Tor is vanishes, we can immediately deduce that the first Tor will vanish. Then will vanish in fact for all R modules N. But well, here should be 7. So and the seventh criterion saying we don't need to consider all the R modules N. It suffices to just consider R quotient by ideals I. And the 8th criterion saying we don't actually need to consider all the ideals I. We just need to consider all the finitely generated ideals I. And because well, we need to make them into a proposition, so there is none empty at every level. Otherwise, they are types, not propositions. So we will see.
Does that have an is 0? I think is 0 might be defined to be non-empty isoform.
I know we have 0 object. I never really used
is 0 might be LTE.
Yeah. Oh, I should say that there's the following. I used a lot of code just to copy and paste from LTE, namely the snake lemma and the first 7 terms of long exact sequences. So our first step is to prove that 5 implies 6 is as long as we can find a free resolution, then the proof is just by using that flat modules means tensing with M is exact. So the category of R modules has enough free objects, hence it has enough projective objects. So if M is an R module, then M copies of R taken as a direct sum is a free module, and there is a canonical surjective map from M copies of R to M by whose M's coordinate. I didn't finish this sentence. Whose M's coordinate is sending R to M times R. Sorry, R times M. And the implementation is so this free is short for associated free module, which is just M copies of R, and from a free it's just the linear map whose M's coordinate is R times M. And the free resolution is if you have an M, then the first map is then the next object should be M copies of R with the first map being epsilon, and we can consider the kernel of epsilon and take the kernel of epsilon many copy of R. And because there is a canonical map from the kernel of epsilon copies of R to kernel of epsilon, this is surjective, and from kernel of epsilon to M copies of R is injective. So now there is so the second map we can call this epsilon 1, and we can play the scheme again. We can consider the kernel of epsilon 1 and take the kernel of epsilon 1 many copy of R and do it again. And we can use this this projective resolution to, and the fact that here you should say tensoring with M is flat, so all higher Tor group will vanish. And the construction of this free resolution is an inductive definition. So it's a bit messy. So we want, for all n, we want to remember what is the previous module and what should be the next module. And we want to prove that the previous module is free and the next module is also free, and we want to map from the next module to the previous module. So this add net rec, the first argument is just what we want to do with this recursion, and the first argument is, well, we want the zeroth module to be just m times copy of R, and we want the next. We want the next module to be. We want the next module to be the kernel of the first map we're going to construct, and we want the free module associated with the kernel of the first module we're going to construct, and well, they are free by construction, and the first and the zeroth map will be the canonical map from from direct sums of R to M. Composed with the embedding from the kernel from the kernel, and the induction hypothesis is, well, if we have now another previous module and the next module, then our new previous module will be the old next module, and our new next module will be the free module associated with the kernel of the old previous map, or the old map by induction. So that will be. So this p dot 2.1 is actually the old next module, and this kernel p dot 2.2.2 is the old map. So the kernel of the old map, then you take the associated free module. Then the new map is just the canonical map composed with the kernel, the embedding of the kernel.
This 2.2.1.2 is somehow terrible.
Yeah,
we've got used to it now, but honestly.
Yeah, so
there's nothing you can do about it.
I mean, a better way is perhaps turning this whole thing into a structure and give it proper names for every field. Then you can instead of .2.2.2, you can just call it p.map or something. But I'm too lazy for that. Yeah. So yeah, using this free module, you can calculate all higher Tor vanishes. And so now we have that flat implies 5, implies 6, implies 7, implies 8, and 5 to 6 to 7 to 8 are all trivial. It's just a specialization. So we finally just need to prove that 8 implies flat. So here we're using the flat in the sense of the force criterion. So yeah, no, it doesn't matter, but we are using the force criterion. So the force criterion, we need to prove that I tensoring with M to R tensoring with M is injective for all finitely generated ideal I. So now let I be a finitely generated ideal, then we can consider the short exact sequence 0 to I to R quotient by I to 0. And this short exact sequence is taken from LTE. And by snake lemma and long exact sequences, the short exact sequence actually induces a long exact sequence. So there will be like there will be Tor of I to Tor of R to Tor of R quotient by I, then to I. So I tensoring with M is actually the zeroth Tor. R tensoring with M is actually the zeroth Tor, and this connecting morphism delta is given by snake lemma. So if anybody else actually want to copy and paste LTE, this is how you do it. Yeah, and LTE proves this beautiful theorem. So the first 7 terms are exact. So now we have that the first 7 terms are exact, but in fact we just need the exactness at delta. But since we assume that tool of one r quotient by I and m is 0, so we know that actually 0 to I tensoring with m to r tensoring with m is exact. And so that means the map from I tensoring with m to r tensoring with m is injective for every finitely generated ideal I. So now we know that 8 implies 4. So yeah, the final square is just how the eight equivalent definitions are equivalent. And that is the end of my talk. Thank you.
Thank you very much.